This is the first question. This is a planning question. This is about determining the relative molecular mass, MR, of a small sample of a volatile liquid. Volatile means a low boiling point, so boil easily, by measuring its mass, so the mass of the volatile liquid, and then you heat it to vaporize it, so liquid to gas, in order to obtain the volume as a gas. So you want the volume of the gas, but you want the mass of the liquid. So this is mass of the liquid, and then this is volume of the gas. So very important to think about not just volume, not just mass, but you got to specify what is what, because it's important that way. Okay, so they say the mass of the liquid because it's difficult to measure the mass of the gas, but if all the liquid goes to gas, then your mass of liquid is equal to mass of gas, and that is why when we have the ideal gas equation, PV equal to nRT, you can rearrange that. So the N refers to the mole of the gas, so that is the mass over the MR of the gas. Then rearrange it, you get MR of the gas is mRT over PV. And equation don't mean anything unless you specify their definitions, their meaning. So M equal to the mass of the liquid, which is equal to the mass of the gas, because you do not lose any mass when you convert from liquid to gas, because there's just boiling or vaporization. You do not lose any mass at all. Okay, it's a physical change. R is molar gas constant, and then the rest are all the usual definitions, but we'll just write all of them down because it's important to know what we're talking about. Yeah, so P equal to pressure of the gas, and finally V is the volume of the gas. And bear in mind that because the MR will be in gram per mole, the mass of the gas will be in gram, all right, whereas this one is in joule per mole Kelvin. This one is in Kelvin. So this one is given in the data booklet all the time, but you don't have data booklet in paper 5. Does not mean that you shouldn't know what you're talking about, all right? Pressure of the gas will be in Newton per meter square or Pascal, and volume of the gas will be meter cube. All right, not that they asked for it anyway. So the next bit of the question. The volume of the vaporized sample depends on temperature and pressure. So in this experiment, you have a volatile liquid, which the mass, you vaporize it, and then you record the volume. So you have the pressure correctly recorded as 101 kilopascal, but the temperature was incorrectly recorded as 50 degrees Celsius, and the correct temperature was 60 degrees Celsius. Bear in mind that despite them giving you the data in degrees Celsius, because of what we actually know from the ideal gas equation, the temperature is in Kelvin. That's why it's important to bear in mind that what is what, right? Okay, so if this is in Kelvin and these are in degrees Celsius, so you do not just use degrees Celsius straight to the ideal gas equation, you have to convert them to Kelvin. All right, and then you need to consider the effect of this different temperature on the gas volume. So that is your Charles' law. I hope you know what Charles' law said. The volume of a gas is directly proportional to the temperature of the gas in Kelvin at constant pressure. All right, so that is Charles' law for you. So how okay would the value of the MR be affected? Okay, so first of all, the correct temperature is higher because it's 60 degrees Celsius. So the correct temperature of 60 degrees Celsius is higher than what was recorded, than the recorded temperature, which is 50 degrees Celsius. So Charles' law, so I'm just stating the effect, right, which is basically, if you just say Charles' law, it doesn't mean anything at all. Okay, so Charles' law states that volume of a gas for a gas at constant pressure, Okay, so you need to think about what is constant, okay, and then what is changing, right? The volume of a gas, I can use this sign, directly proportional to the temperature of the gas in Kelvin. All right, so I've just stated those things, but what is the effect then? Okay, therefore higher temperature of 60 degrees Celsius means greater volume of gas in reality, okay, not what they are recorded. So in reality, so what can we say? So you need to compare the calculated MR for 50 degrees Celsius versus 60 degrees Celsius, right? I started by saying the one with higher temperature would mean greater volume of gas. So if you go back to the equation, MR equal to MRT over PV, MR equal to MRT over PV. So at higher temperature, so following on from what I just said previously, so greater volume of gas, and so we expect the MR to be lower despite the temperature being higher, because we already take into account that, you know, temperature and the volume of gas can change. If you want, you can compare the two. So what am I saying? What I'm saying is that you have MR is proportional to the temperature over the V, which is at 60 plus 273. Okay, and let me think. The temperature itself is proportional to that, so maybe I shouldn't be thinking about that at all. Hang on, let me think through this problem first. So Charles' law says that for a gas at constant pressure, volume of a gas is directly proportional to temperature of a gas in Kelvin. Okay, so if my temperature is higher, my volume is higher. So if my volume is higher, my MR will be lower. So therefore the MR for 60 degrees Celsius would be lower. I think that should be alright. Let me think. I think so, yeah. Actually, I think I can make it sound a bit better, okay? So this is the actual temperature, but this is what you have incorrectly recorded, okay? So this is your reading, okay? So this is your reading at 50 degrees Celsius, at 60 degrees Celsius, but you have incorrectly used 50 degrees Celsius, so that is the incorrect thing. But as a result of the actual temperature being 60 degrees Celsius, your volume is actually bigger than what it should be. If the volume is bigger than what it should be, the MR will be lower. Okay, so maybe I should say at actual higher temperature, since the volume of gas is greater, then the MR will be lower. So I think there's a confusion between this question actually, and I was a bit confused at that time. I mean, when I first started this question, was that this is the temperature you have used for your reading in your equation, but in reality it's actually higher. So in reality the volume is higher, and therefore the MR is actually lower. Okay, so I hope that makes sense then. So next question. So you maintain the temperature at 60 degrees Celsius, which is the actual temperature, but you increase the pressure. So this is the new change. So previously it was 101 kilopascal. So from 101 kilopascal to 110 kilopascal. Would this have an answer that was nearer to the true value? Explain the answer. So this is a different type of scenario. State and explain. It's basically the same kind as the previous question. All right. So at constant temperature, so we know at constant temperature, when pressure increases, the volume of gas decreases. This is actually Boyle's law. Okay, or you can say PV equal to constant for gas at constant temperature. So at constant temperature. So what do we know so far? So when your pressure is increased, your volume of gas will actually decrease. Okay, your volume of gas will actually decrease. So volume of gas decrease would be the opposite of that, and that would mean the MR would be higher. So the fact that this was one mistake and this didn't follow through from that mistake. But then we also have to remember that this is only true where your system can change the volume, can expand and contract at the same time. But what we have in this kind of setup is that you have a fixed container to hold the volume of the gas, which means that the volume doesn't change, and therefore we are not essentially just looking at Boyle's law on its own. So when we just increase the pressure here, the volume of the gas doesn't exactly change because you are not in a balloon which can go increased volume or decrease in volume. So that's why I was a bit in a bit of a dilemma, because where the PV is equal to constant, that means there will be no change. But we really need to be thinking about the change as well as the system that we are in at the moment. So when pressure increase, so the volume will remain the same because the volume of the container doesn't change. It's the container itself that holds the gas itself doesn't change. So from the equation itself again, so MR equal to MRT over PV. So it relates to the previous question, as this is part 2, but whatever change that was here, it's not essentially the change that is given in this question. So when pressure increase, and therefore the MR will decrease. When pressure increase, then the MR would decrease. Is that true? Let me see. So as the volume of gas decreases, we can see that it's the opposite effect to what we saw in the previous question when we had higher temperature in reality. So when you have lesser volume of gas, that means that the MR would be higher. So the lesser volume of gas, therefore the MR would be higher. So that is actually answering the first part of the question, as the second part of the question, which is explain your answer, but we haven't really stated the first part of the question yet. Would this have an answer that was nearer to the true value? So previously we have the MR that will be lower, and here the MR would be a bit higher. So in reality, so this give nearer value to the true value of the MR. Okay, so in this kind of question where you state and explain, or where they ask you something and then explain, you gotta consider that you need to answer each and every bit of the question. So even though it's only 1 mark, so that's why I went back and numbered them, so you can see exactly that there are how many different parts of the question that you need to fulfill, before you move on. All right, and it's something that a lot of students are very complacent about, and they don't bother because you not necessarily have time to check back your work, so you should check them as you go along each part. So this is the experimental design bit. When you determine the MR of hexane, the boiling point is 69 degrees Celsius, so that is lower than the boiling point of water. It's actually quite low, but it is a liquid at room temperature and pressure, because room temperature and pressure is 25 degrees Celsius, 298 Kelvin. So you have a Victor Meyer tube that you can use. You have a long tube. You have a bulb at the base, in which you can vaporize the sample. So this is the bulb at the base. You have the liquid, I guess, and then it will get vaporized. All right. So what do we know here? The tube is surrounded by another, which can be used to heat the content of the first tube. So I think this is the small sample tube that is put inside. Inside where you heat the outer bit, and then it will vaporize the inner bit, which will vaporize the hexane with the low enough boiling point, and when we vaporize the liquid hexane, it's going to go into a gas. And as part of your measurement, you wanted to measure the volume of the gas, so this is about a gas collection apparatus. All right. So a small sample tube is inserted at the top of the Victor Meyer tube. So yep, okay. And then that small sample tube is small enough to fit inside the Victor Meyer tube. You fall onto the free sand, which is hot. Okay. The sand will cushion its fall because you're putting glass into glass, so you don't want the glass to break. Okay, so the stopper is then replaced. You need a stopper because you do not want the gas that get vaporized. You don't want it to escape out the top, because then whatever gas that you collect, the volume won't be accurate then. Okay. The hot sand causes the hexane to vaporize. It expels the air contained in the Victor Meyer tube. So how the apparatus should be heated, so that's the first bit. And then you gotta allow the air to be expelled, so that means you need the air to be expelled, and then you can collect and measure the sample of hexane. So there's bound to be a bit of air inside, and as the hexane get vaporized, the gas will push against the air, and the air will be collected as well. So it's all part of the gas collection apparatus. Hexane is insoluble in water because it's a non-polar organic molecule. So what I'll have is, I don't think that thing is very well drawn, but anyway, so I will have my graduated measuring cylinder, which is not the most accurate thing in the world. And if you want really accurate stuff, you can use a pipette if you want to. But we're just doing gas collection, and if you have done any practical experiments involving gas collections, you would know that we can sometimes use graduated measuring cylinder to collect gases as well. All right, so there's your gas collected inside, and then this is just your water bath. Well, it's not water bath, it's just a water basin. Okay, because we are not heating it. All right. In fact, I think any suitable gas collection technique or apparatus would be okay, because like I said, you might be thinking about using pipette, which is far more accurate, and it's entirely acceptable as well. Okay. How would we heat this one up? So this is glass, right, and we want to heat up the sand. So I assume that we are not going to put a fire here, because inside here will be air, and then air is a poor conductor of heat. So if you heat here, and glass is a poor conductor of heat as well, so you gotta heat the glass and the air. Not a lot of heat is gonna reach the sand, so you don't want that. So perhaps we can have water, and then you can have water bath to heat up the sample. And we know that we can use water bath to heat up samples in glass tube or in beakers or whatever, because they are quite safe. Yeah. So how the apparatus should be heated, like a water bath, which is all right. How you're gonna collect the gas, which I just did with a collection over water there. So my connection should have been a bit better, but anyway, that's the best I could do. Suggest one hazard. So usually with hazard thing, right, they will give you a table telling you about hazard, like what are the hazards associated with it. But hexane is one of those things, right? It's a petroleum product. It's a hydrocarbon, C6H14. And you should know, as with all petroleum product hydrocarbons, they are extremely flammable. Okay, it is extremely flammable. So you do not put a naked flame near a flammable liquid at all. Okay, so keep away. No, actually they don't say what are the safety precautions, so I do not need to say keep away from naked flame. In fact, they just want you to talk about the hazard. All right, so it is a flammable liquid. You can probably talk about the breathing associated breathing problem as well. As with all the petroleum products, you do not want to be sniffing around petroleum products. Now, they don't smell good when you go and fill out a petrol at all. Okay, so carcinogenic in the long run, but carcinogenic is not an immediate effect, so it's not an immediate hazard. All right. With the gas collection apparatus, so they kind of give you the hint there. So you need a gas collection apparatus. You do have expel air. So in addition to whatever volume of gas that you are collecting, you do have a bit of air that you'll be collecting at the beginning as well. And that is what this question is. Will be collected before the hexane is introduced, meaning to say before you actually start gathering the volume of hexane, you will actually collect a bit of air as well. Yeah, okay. So why is this? So at high enough temperature, at high temperature, I guess, whenever you heat gases up, air can expand. All right. And as you know, like there's a principle of hot air balloon anyway. Like you heat up the air, and then if it makes the balloon go big, and then it will float up because of the pressure exerted against the outer pressure resulting from the hot air. Yeah, okay. So air expands, and this rises up the tube, and gets expelled first into the gas collection apparatus. As you can imagine, the air itself is already gaseous, but your hexane is still a liquid. So which one do you think will be easier? The expansion of the gas, the air, which are already mixture of gases, or would it be the vaporization of the liquid hexane, which involve breaking the weak van der Waals forces again? All right. So at which stage should the sample tube be dropped into the Victor Meyer tube? So you want it to heat up, right? So as you know that that you will have a bit of air inside, and you need to collect that first reading, and for as long as you still have air, or the gases that are being present, they are being expelled, you will keep on seeing bubbles there, and then you will record the reading, because whatever volume that is, there is your initial volume reading, because whatever there is there will just be air without any hexane, because you haven't dropped any hexane in. So that's your first reading. So when you drop the hexane in will be when there is no more movement of this reading. That is a result of no more bubbles of the air being expelled. So that is when we can drop the hexane in, and then we can start reliably measuring the volume of hexane vapor being given out. All right. So at which stage? So when no more air is being expelled into the gas collection apparatus, and you can tell this as indicated by normal bubbling, because it's quite hard to read on the graduated gas syringe or graduated measuring cylinder or burette, but should be able to tell by just looking at normal bubbles of gas as you collect it over water. Yeah, normal bubbling of gas being collected over water. But again, these are all just experimental observations and techniques that you would have known anyway. Okay. Only then you add the hexane. Okay, when no more air, only then we add the hexane in that small liquid vial, yeah, into the hot sand. Okay, this is the last bit of this planning question. It's for 3 marks, which means quite a bit of things that they want here. They want measurements, so it's plural. You need to make measurement in order to determine the relative molecular mass of hexane. So just now remember that MR is MRT over PV. So what do we need to measure? Okay, so we need to know how much mass of hexane have been evaporated, right? So remember just now at the very beginning, so the mass of liquid is the same as the mass of gas, but it's very hard to measure the mass of gas, and because we know there's no change of mass when you vaporize something, conservation of mass theory. Yeah, so we need to know the mass of the liquid, and the liquid is inside a small sample tube with a hexane. So if you know what is the mass that you put in the tube plus the hexane, and you have the mass of the tube at the end. Okay, that is the difference will give you the mass of the liquid hexane being burned. All right, so the first one is to do with the mass of the hexane being burned. So it's the mass of tube and liquid hexane. And then the second one will be the mass of empty tube. Okay, so after all hexane has been vaporized, so either at the end of the reaction, okay, I mean at the end of that vaporization experiment, yeah, okay, so the difference between these will give you the mass of hexane, the mass of the hexane vaporized, okay, and that is not what you measure, because that is what you calculate from two different mass measurements. All right, and what else do we need? So we have the mass, the molar gas constant is constant, obviously, and we also need the temperature. So the temperature of the hot water bath, which is assumed to be the temperature at which this thing will happen. Of course, it will need to be higher than the boiling point of hexane, otherwise the hexane won't vaporize, right? If it's just water at room temperature, the hexane won't vaporize at all. Okay, and then the fourth one will be the pressure. So you need to know the pressure of the system, the pressure of the gas. Okay, and lastly, you will need to measure the volume of the hexane gas being produced. But remember that they already kind of guided you that you already have a bit of expel air, so you don't take it from zero. So you need to take it from the moment when there is no more bubbles being produced before you add in the hexane vial into here. So that is your initial reading. So that's the volume of the volume reading before hexane was added. And of course, then as the hexane get vaporized, this volume will increase again, and this level will fall down, and then you have the volume reading after hexane was added. Okay, so you will have the volume reading on the I guess graduated measuring cylinder, or burette, or gas syringe. I mean, which depending on whichever one you use, gas syringe or burette. Before hexane was added, and then after hexane was added, basically the vial containing the hexane was added and completely vaporized. So until no more gas is being collected after all the hexane has been vaporized. All right, so that marks the end of this first planning question, which is not